Open channel flow. This topic introduces the concept of open channel flow, which is characterized by the presence of a free surface exposed to the atmosphere. Unlike flow in closed conduits, the pressure at the water surface is always equal to atmospheric pressure. Common examples include rivers, canals, and irrigation channels. The analysis of this type of flow is essential in civil and water resources engineering. The main focus is how gravity affects velocity, depth, and flow profiles.
Lesson Plan: Fluid Mechanics 2. This section shows the position of open channel flow within the overall Fluid Mechanics 2 course. Previously, topics such as the Navier-Stokes equation, external flow, and compressible flow have been discussed. This chapter serves as a bridge toward the discussion of turbomachinery in the next chapter. The sequence indicates that understanding open channel flow requires a strong foundation in fluid mechanics. With this structure, students are expected to see the interconnection among topics in a systematic way.
Learning outcome. The learning outcomes are formulated to ensure that students understand the differences between open channel flow and pipe flow. In addition, students are expected to recognize different flow regimes and their characteristics. The ability to predict hydraulic jumps and calculate the dissipated energy is an important competency. Methods of measuring discharge using sluice gates and weirs are also included. Overall, these outcomes emphasize both conceptual understanding and practical application. Open channel flow. This image shows a real example of open channel flow in a meandering natural river. The presence of a free surface is the main feature that distinguishes it from closed conduit flow. The meandering shape also indicates the influence of topography on the flow pattern. In natural systems, velocity and depth can vary significantly along the channel. This illustration emphasizes that the concepts discussed are not only theoretical, but also strongly observed in nature. Characteristics of open channel flow. Open channel flow always has a free surface exposed to the atmosphere, which means the pressure there is known and constant. The system can be natural, such as rivers, or man-made, such as spillways and canals. The flow behavior is strongly influenced by gravity and the bed slope. Small changes in slope or roughness can significantly alter the depth and velocity. Therefore, the analysis of this flow always considers geometry and terrain conditions.
Check your understanding number 1. This question emphasizes the understanding of velocity distribution in a trapezoidal channel cross-section. The maximum velocity does not occur near the walls because of friction effects. The center of the channel usually experiences the least resistance, so the velocity there is the highest. This concept is important for understanding two-dimensional velocity profiles in real flows. The correct answer reinforces the intuition about the influence of boundaries on flow.
Velocity contours in open channels. The velocity contours show that the velocity distribution is not uniform across the channel cross-section. The maximum velocity occurs near the center and decreases toward the walls and the bottom. This pattern is caused by friction between the fluid and the solid boundaries. The contours, normalized by the average velocity, help compare different flow conditions. This visualization is important to understand why the uniform velocity assumption is often only an approximation.
Uniform flow characteristics. Uniform flow is characterized by a constant flow depth along the channel. The average velocity also remains constant because there is no net acceleration along the flow direction. This condition can only occur if the bed slope is also constant. In this situation, gravitational forces and friction forces are in balance. The uniform flow model is very important as a basis for many channel design calculations. Flow transition dynamics. In practice, flow is not always uniform and often experiences changes in conditions. Slowly changing flow is called gradually varied flow, while abrupt changes are called rapidly varied flow. Between these two conditions, there are regions of uniform flow before and after the transition. These changes are usually triggered by variations in geometry or channel slope. Understanding this classification is important to select the correct analysis method. Hydraulic radius concept. The hydraulic radius is defined as the flow area divided by the wetted perimeter. This quantity is not the same as the geometric radius and often leads to misconceptions. The hydraulic radius is used to represent how efficient a cross-section is in conveying flow. The larger its value, the smaller the relative influence of friction. This parameter is very important in empirical formulas, such as the Manning or Darcy-Weisbach equations. Hydraulic radius for channel geometries. The hydraulic radius depends on the channel cross-section shape and the water depth. In a circular channel, its value changes with the wetted angle and the wetted perimeter. In a trapezoidal channel, the combination of bottom width and side slopes determines the flow area and wetted perimeter. For rectangular channels, the ratio between width and depth becomes the main factor. For thin liquid films, the hydraulic radius can be approximated directly by the flow depth. Check your understanding number 2. This question emphasizes that in a circular channel, the hydraulic radius is not constant and varies with water depth. The two main parameters that affect it are the angle subtended by the water surface and the wetted perimeter. When the depth increases, both of these quantities also change. This makes the flow characteristics in circular channels more complex than in simple channels. This understanding is important for design analysis and discharge calculations. Mach and Froude numbers. The Mach number is used in compressible flow to compare the flow velocity with the speed of sound. In open channel flow, the equivalent parameter is the Froude number, which compares the flow velocity with the wave speed. The categories subsonic, sonic, and supersonic are analogous to subcritical, critical, and supercritical. The wave speed in open channels depends on gravity and flow depth. This concept helps classify flow behavior dynamically. Subcritical and supercritical flow. Subcritical flow occurs when the flow depth is greater than the critical depth and the velocity is relatively low. In this condition, gravitational effects dominate over inertia. In contrast, supercritical flow has a depth smaller than the critical depth and a higher velocity. In this case, inertia dominates over gravity. The transition between these two conditions marks a very important change in the flow regime in hydraulic analysis. Wave generation in open channels can be generated when a moving plate pushes the fluid. This motion causes changes in depth and velocity that propagate as a wavefront. The analysis can be performed using a control volume moving with the wave. Within this control volume, pressure and velocity change in a coupled manner. This phenomenon shows the close relationship between wave dynamics and the base flow. Supercritical flow through a sluice gate. When water flows under a sluice gate, the flow can change from subcritical to supercritical. Downstream of this section, a hydraulic jump often occurs. This jump converts the supercritical flow back into subcritical flow. The process is accompanied by significant energy dissipation. This mechanism is very important to stabilize the downstream flow conditions. Correct answer, C, to dissipate energy and stabilize flow conditions by converting supercritical flow back to subcritical flow. Explanation of incorrect options. Option A, the hydraulic jump reduces velocity and dissipates energy. It does not increase the velocity of supercritical flow. Option B, a hydraulic jump converts supercritical flow to subcritical flow, not the other way around. Option D. The primary function of a hydraulic jump is energy dissipation and stabilization, not reducing flow depth for smaller channels.
Hydraulic jump observation on a plate. A simple experiment with a plate shows how a hydraulic jump can form naturally. On a right side up plate, gravity helps create a clear hydraulic jump. On an upside down plate, this phenomenon does not occur because gravity no longer stabilizes the flow. This difference shows the important role of gravity in the formation of a hydraulic jump. This example makes it easier to visualize a concept that is often abstract.
Specific energy in open channels. Specific energy is defined as the total mechanical energy per unit weight of the fluid relative to the channel bottom. This quantity consists of velocity, flow depth, and elevation components. By using the energy line, the total energy of the system can be visualized along the channel. This concept is very important to analyze flow changes due to contractions or geometry variations. Specific energy is a key tool for understanding hydraulic jumps and critical flow. Specific energy versus flow depth. For a given discharge, there is a characteristic relationship between specific energy and flow depth. At a certain point, the specific energy reaches a minimum value known as the critical condition. For depths above this point, the flow is subcritical, while below it, the flow is supercritical. This graph shows that one energy value can correspond to two different depths. This concept is very important in analyzing flow transitions and hydraulic structure design. Flow through a sluice gate. Upstream of the sluice gate, the flow has a greater depth and lower velocity, which makes it subcritical. After passing under the gate, the flow depth decreases significantly and the velocity increases, making it supercritical. This change indicates the existence of two alternate depths for the same discharge. The sluice gate acts as a control element that triggers changes in flow energy and momentum. This phenomenon is very important in the design of flow control structures. Total energy in open channel flow. The total energy in a flow consists of elevation, pressure, and velocity components measured from a reference datum. The energy line represents the total mechanical energy available along the flow. Any change in depth or velocity will change the position of this energy line. This concept helps visualize how energy is distributed in the channel system. With this approach, the analysis of energy losses becomes more systematic.
Check your understanding number 4. This question tests the understanding of the energy components that make up the total energy in a flow. The three main components are elevation, pressure, and velocity. All of them are always measured relative to the same reference datum. Misunderstanding any of these components can lead to incorrect energy analysis. Therefore, mastering this basic concept is crucial in fluid mechanics. Total energy at two sections in open channels. Between two sections along a channel, the total energy is usually not the same because of energy losses. These losses are mainly caused by friction and the effect of channel slope. The energy line decreases in the flow direction as an indication of energy dissipation. This energy difference can be calculated to determine the head loss. This analysis is the basis for evaluating the hydraulic performance of a channel. Uniform flow in open channels. In uniform flow, the depth, velocity, and channel slope remain constant along the flow length. The energy loss per unit length is equal to the elevation drop of the channel bed. This indicates that the energy line and the channel bed are parallel. This condition only occurs if the geometry and roughness of the channel do not change. This model is very useful as an initial approximation in channel design. Manning coefficient for open channels. The Manning coefficient represents the roughness of the channel surface. Artificial smooth channels, such as glass or metal, have small Manning values. Natural channels with gravel, stones, or vegetation have much larger values. The larger the Manning value, the greater the flow resistance. Therefore, the selection of this value has a strong influence on discharge and velocity calculations. Semicircular cross-section in open channels. A semicircular cross-section provides the minimum wetted perimeter for a given flow area. With a smaller wetted perimeter, frictional resistance becomes lower. As a result, the hydraulic efficiency becomes higher compared to other shapes. This design allows the maximum discharge for given conditions. Theoretically, this shape is considered one of the most efficient cross-sections. Correct answer: B. It minimizes the wetted perimeter for a given flow area, reducing flow resistance and energy losses. Explanation of incorrect options. Option A. Maximizing the wetted perimeter increases flow resistance and energy losses, making this approach inefficient for channel design. Option C. While depth affects pressure head, the semicircular design optimizes efficiency by reducing the wetted perimeter, not by directly increasing the pressure head. Option D. Hydraulic efficiency in this context is achieved by minimizing resistance and energy loss, not necessarily by increasing flow velocity. Rectangular open channel flow. In a rectangular channel, there is an optimum depth condition for achieving maximum efficiency. This optimum depth occurs when the flow depth is equal to half of the channel width. Under this condition, the relative frictional resistance becomes minimal. As a result, the discharge that can be conveyed becomes maximum for a given area. This principle is often used in the design of simple artificial channels. Variation in hydraulic radius and flow rate. Changes in the ratio between width and depth affect the hydraulic radius. As this ratio increases, the hydraulic radius first increases and then decreases. This leads to the existence of an optimum condition for flow efficiency. The maximum discharge does not occur at extreme conditions, but at an intermediate one. This graph shows the importance of geometric proportions in channel design. Flow rate variation with aspect ratio. The flow rate reaches a maximum value at a certain aspect ratio that provides the highest hydraulic efficiency. If the channel width keeps increasing while the depth decreases, the flow resistance actually increases. This condition causes the discharge to decrease even though the cross-sectional area may still be large. Therefore, there is a geometric proportion that is most efficient for conveying water. This principle is very important in artificial channel design. Trapezoidal channel parameters. A trapezoidal channel is defined by the bottom width, flow depth, and side slopes. These parameters together determine the flow area and the wetted perimeter. The hydraulic radius then depends directly on this geometric combination. This shape is widely used because it is relatively easy to construct and structurally stable. In addition, it provides a good compromise between flow capacity and construction cost. Optimal trapezoidal channel design. The most hydraulically efficient trapezoidal shape resembles half of a hexagon. This configuration minimizes the wetted perimeter for a given flow area. As a result, frictional resistance is minimized and efficiency increases. The proportions between side slopes and depth must be carefully arranged to achieve this condition. This design is the result of optimization between flow performance and structural stability. Check your understanding. Number 6. This question reinforces that the most efficient trapezoidal shape resembles half of a hexagon. The key to this efficiency is the minimization of the wetted perimeter. With a smaller wetted perimeter, energy losses due to friction can be reduced. This directly increases the flow capacity for the same conditions. This concept is important to ensure hydraulically optimal design. Advantages of trapezoidal channels. Trapezoidal channels are relatively inexpensive to construct because the excavation and shaping process is simple. This shape also provides good flow performance with moderate resistance. In addition, it is flexible for various applications, such as drainage, irrigation, and flood control. The stability of the side slopes is also easier to maintain compared to vertical walls. Therefore, this shape is very popular in engineering practice.
Gradually varied flow in open channels. In gradually varied flow, the depth and velocity change slowly along the channel. The energy line decreases gradually due to energy losses caused by friction. These changes are usually influenced by variations in bed slope or downstream boundary conditions. The analysis is performed using a differential approach along the channel. This concept is important for predicting water surface profiles in rivers and canals. Uniform flow in rivers. Uniform flow in rivers is characterized by constant water depth and cross-sectional area along the stream. In this condition, the bed slope is approximately equal to the energy slope. The balance between gravitational and frictional forces keeps the flow stable. Rivers that are close to this condition are often used as references in hydraulic analysis. This model simplifies the calculation of discharge and flow velocity. Liquid surface profiles and slopes. The water surface profile is strongly influenced by the channel bed slope. On steep slopes, the flow tends to be faster and often becomes supercritical. On mild slopes, the flow is usually slower and subcritical. The critical slope represents the boundary condition between the two regimes, while an adverse slope can produce backwater effects. This classification helps predict the shape of water surface profiles in practice. Correct answer. B. It causes the flow to oppose gravity, often resulting in backwater effects and reduced energy. Explanation of incorrect options. Option A. Adverse slopes do the opposite of increasing velocity. They create conditions where the flow resists gravity, slowing the flow, and sometimes causing backwater effects. Option C. Critical slopes, C, not adverse slopes, are responsible for maintaining uniform energy distribution and steady flow. Option D. Adverse slopes do not minimize energy loss or enhance efficiency. Instead, they can create inefficient flow conditions and energy dissipation. Liquid surface profiles and depths. In uniform flow, the water surface corresponds to the normal depth. In critical flow, the water surface is at the critical depth, which marks the boundary between flow regimes. Different water surface profiles appear depending on the relationship between actual depth, normal depth, and critical depth. The comparison of these three depths forms the basis for classifying flow profiles. This concept is very important in gradually varied flow analysis. Classification of surface profiles in gradually varied flow. Surface profiles are classified based on the bed slope and the relationship between actual, normal, and critical depths. On steep slopes, the flow usually has a Froude number greater than 1 and is supercritical. On mild slopes, the flow tends to be subcritical, with smoother depth variations. Critical profiles appear when the slope and energy conditions are exactly at the transition boundary. This classification simplifies the analysis of water surface shapes under various field conditions. Common surface profiles in open channel flow. On mild and adverse slopes, the flow often transitions through hydraulic jumps or free outfalls. On steep slopes, the flow can change rapidly from one condition to another. Combinations of slope changes can produce various water surface profile shapes. Each profile represents a different balance of energy and momentum. This understanding is important to predict flow stability and erosion potential. Gradually varied flow profile.
In this profile, the water depth increases gradually along the channel. The flow remains above the critical depth and approaches the normal depth downstream. The slow change indicates that friction and slope effects are acting in balance. Such a profile is often found in long rivers or canals with mild slopes. Analyzing this profile helps estimate the water surface elevation along the channel.
Rapidly varied flow characteristics. Rapidly varied flow occurs when there is a sudden change in geometry or flow conditions. These changes are usually localized over a very short distance. The most common examples are hydraulic jumps and wave formation. In this region, the hydrostatic pressure assumption is no longer valid. This phenomenon is accompanied by large energy losses and strong turbulence.
Check your understanding. Number 8. This question emphasizes that rapidly varied flow is caused by sudden changes in cross-section or flow conditions. The effects are local and often accompanied by hydraulic jumps. This phenomenon cannot be analyzed using the gradually varied flow approach. Understanding this difference is important to choose the correct analysis method. The correct answer shows an understanding of the basic nature of rapidly varied flow.
Flow dynamics in rapids. Rapids are an example of a combination of gradually varied flow and rapidly varied flow. In some sections, hydraulic jumps and strong turbulence occur. Changes in velocity and depth occur alternately along the channel. These conditions cause significant energy dissipation. This phenomenon explains why flow in rapids appears very dynamic and unstable.
Hydraulic jump and energy transition. A hydraulic jump occurs when supercritical flow changes into subcritical flow. During this process, the depth increases suddenly and the velocity decreases drastically. This change is accompanied by very strong turbulence. The energy line shows a sharp drop, indicating a large energy loss. This phenomenon is often used to protect downstream structures from erosion.
Energy dissipation in hydraulic jumps. Hydraulic jumps cause a large loss of mechanical energy in the flow. This loss can be seen as a reduction in specific energy before and after the jump. The dissipation ratio is used to express how much fraction of energy is lost. This process is very important to reduce the downstream flow velocity. As a result, the risk of damage and erosion can be significantly reduced. Types of hydraulic jumps. There are several types of hydraulic jumps classified based on the Froude number and turbulence level. Weak and undular jumps have small energy losses and relatively smooth waves. Oscillating and steady jumps have moderate energy dissipation and are often used in engineering design. Strong jumps are highly turbulent and very effective in dissipating energy. However, this type requires a large water depth and is therefore not always economical.
Answer B. Weak and undular jumps. Explanation. A. Strong jumps. This is incorrect because strong jumps are characterized by high energy dissipation and turbulence, which is opposite to the description of low energy dissipation in the question. B. Weak and undular jumps. This is the correct answer, as weak and undular jumps are described as having low energy dissipation and small rollers, typically occurring at low Froude numbers. C. Oscillating and steady jumps. This option is incorrect because oscillating and steady jumps are associated with moderate to high energy dissipation, which is different from the characteristics mentioned in the question. D. Hydraulic jumps. While hydraulic jumps encompass a range of jump types, this answer is too general and does not specifically address the description of low energy dissipation and small rollers in weak and undular jumps.
Weirs as flow control devices. Weirs are used to control and measure discharge by allowing water to flow over an obstruction. When water passes over the crest, part of the mechanical energy is dissipated. This process reduces the downstream velocity and stabilizes the flow. Weirs are widely used in rivers and irrigation channels to control water levels. In addition, the relationship between head and discharge can be used for measurement purposes. Flow through underflow gates. Flow under gates can produce subcritical or supercritical conditions depending on the gate setting and downstream depth. If the downstream depth is greater than the critical depth, a drowned outflow condition occurs. In this case, the supercritical flow is suppressed and does not fully develop. The flow path is strongly influenced by specific energy and boundary conditions. This phenomenon is important in controlling water levels and discharge. This section serves as a transition toward the detailed discussion of different types of underflow gates. The illustration shows the general configuration of flow around a gate and the possible depth changes. The focus is on visualizing the flow path and contraction region. This image helps connect the specific energy concept with the actual flow shape. With this visualization, the flow mechanism under a gate becomes easier to understand. Common types of underflow gates. There are two main conditions, namely free outflow and drowned outflow under a gate. In free outflow, a narrow, high-velocity jet called a vena contracta is formed. In drowned outflow, turbulence and downstream resistance cause greater energy losses. Although more stable, the drowned condition has lower efficiency. Various types of gates, including drum gates, are used to control these conditions in practice. Discharge coefficients for underflow gates. The discharge coefficient indicates how efficiently flow can pass under a gate. Under free outflow conditions, the discharge coefficient is higher because there is no downstream resistance. When the downstream depth increases, the flow becomes drowned and the discharge coefficient decreases. This change reflects the increase in energy losses in the system. Therefore, downstream boundary conditions strongly affect gate performance. Check your understanding. Number 10. This question emphasizes that when the downstream water depth increases, flow efficiency decreases. This condition is known as drowned outflow. In this situation, part of the energy is lost due to turbulence and additional resistance. As a result, the discharge coefficient becomes smaller. Understanding this is important in evaluating the performance of hydraulic structures. Specific energy and flow depth. This graph shows how flow energy changes with water depth. The lowest point represents the critical condition, which separates two flow regimes. Above it, flow is deeper and slower. Below it, flow is shallower and faster. Flow over a bump in the channel bed. When flow passes over a bump in the channel bed, the specific energy decreases at the crest of the bump. If the upstream condition is close to critical, the flow can be forced to become critical over the bump. This change causes localized variations in depth and velocity. This phenomenon is often used as a flow control device. The analysis shows the close relationship between bed geometry and flow regime. Flow over a broad-crested weir. On a broad-crested weir, the flow passes over the crest with relatively smooth depth changes. Over the crest, the flow usually reaches critical conditions. The discharge is determined by the upstream head above the crest. This characteristic makes this type of weir stable and predictable. Therefore, it is widely used in irrigation and flood control systems. Flow over a sharp-crested weir. On a sharp-crested weir, the flow separates from the crest and forms a distinct nap. The discharge strongly depends on the upstream head above the crest. Because this relationship is very consistent, this type of weir is often used for discharge measurement in laboratories. The separated flow also makes visual observation easier. This makes it very suitable for experimental purposes. Triangular V-notch weir plate. The triangular weir is very suitable for measuring small discharges because of its high sensitivity to changes in water head. The triangular shape makes the relationship between head and discharge more responsive. The notch angle determines the flow characteristics and measurement range. This device is widely used in irrigation, hydrology, and laboratory experiments. Its main advantage is high accuracy for low flow rates.
Answer B. Triangular notch weir. Explanation. A. Venturi meter. This is incorrect because a Venturi meter is designed to measure flow rates over a wider range, not specifically for low flow rates with a triangular geometry. B. Triangular notch weir. This is the correct answer, as the triangular notch weir is ideal for accurately measuring small flow rates, thanks to its triangular shape and adjustable flow measurement based on the notch angle. C. Orifice plate. This option is incorrect because orifice plates are typically used for higher flow rates and do not have the triangular geometry specific to the question. D. Flow channel. This is incorrect, as a flow channel does not specifically refer to an instrument with triangular geometry for precise flow measurement.
References. This section lists the main source of figures and materials used in the lecture. The book by Chengel and Chimbala is one of the standard references in fluid mechanics. Using this source ensures that the presented material is consistent with internationally recognized engineering literature. This reference can also be used by students for further independent study. In this way, academic quality and conceptual consistency are maintained.